So in the previous video, we have learned how to train a single neuron model, right? A single neuron model. So in this case, we recapped or we revised what stochastic gradient descent is, some basic, some chain rule, right? Very basic stuff in calculus, right? The most important thing in neural networks are multi-layered perceptrons. This video and the next couple of videos are probably the most important videos in the whole of deep learning. Because in this video and the next couple of videos, we will learn how to train a multi-layered perceptron, which is the most important stuff. So through the next three videos, we'll learn an algorithm called back propagation algorithm. Back propagation algorithm. Don't worry about the terminology. It is nothing but it's just an extension of what we learned in a single neuron model. It's just chain rule with SGD and a couple of more very simple tricks, nothing very fancy. It's very, very straightforward, right? But it's important to follow this in detail. That's why I'll go slightly slower in this video so that you understand the notation, you understand the mathematics. I will go into some notation that we have already seen earlier. I'll reuse the notation that we have used, that we have learned on how to represent a multi-layered perceptron. So please bear with me. I'll go slightly slow in this so that you understand all the details, right? So let's start here. Imagine you're given a data set of xi comma yi, right? Where let's say xi belongs to R4, four-dimensional data, and yi belongs to R, right? Here we want to train a multi-layered perceptron, and this problem is a standard regression problem, right? In a standard regression problem, a simple loss function that we have is squared loss, right? A very, very simple loss function that we have is nothing but squared loss. So we'll use some of these and understand how to train a multi-layered perceptron. Okay, so let me first draw a multi-layered perceptron with the notation that we saw earlier, right? If this is a xi has four features or four dimensions. Sorry, this is xi3. Sorry, this is xi3 and this is xi4. So I have four features, this four together. So this whole thing is nothing but my xi, these four things together, right? So let's draw a simple neural network, right? This is my f11 because this is my first layer, right? This function is f12, this function is f13. So we have introduced this notation in one of the previous videos. So go check it out if you've forgotten some of these details, because we need this notation to understand how things are working out, right? So this is layer 2 where I have two neurons, f22 and f21, and I have layer 3 where I have a neuron which is f31. The activation functions are f11, f12, f13, so on and so forth. Now these inputs, all inputs are connected here, right? So there are four, since there are four inputs here and four neurons, so this is layer 1, right? This is layer 1. Okay, let me not put a circle there. This is layer 2 and this is my output layer and this is my input layer, right? This is my output at the end of everything. So here I have again all these four inputs connecting to my second neuron here. Okay, let me just redo it properly. Okay, so all of them connected to my second neuron and similarly to my third neuron, all right? So here again, I have this and this connections, this connection and this connection, this connection, this connection, these two connections, and here is my output, right? Here is my output. Now the output that I get is yi hat, right? Because when I input xi, right, I get yi hat as my input, as my output. So my output here is yi hat. Now I need a loss function, right? So just the way we have seen in a single neuron model, right? My yi goes into a loss function, right? So similarly here also I have a loss function here. Let me just represent it with a L here, right? So this loss function is a loss function on yi and yi hat. This yi hat is the output of f31. Yi is what I have. So if you recall, if you understand, the xi's are in my data set, my yi is also in my data set, right? What is my data set? My data set is xi and yi, right? As you can see here, xi and yi are my data sets. Yi hat is the predicted value that I get. So as we have seen, the weights here are represented with with W with superscript 1. I'll call it W1. This is basically, there are 12 weights here, right? Because there are 4 values here and there are 3 values here. And as we have seen earlier in the notation, this can be represented as a 4 cross 3 matrix. Similarly, the weights here are called W2, right? These are W1. These are the weights here. The weights here, let's call them W2. And this is a 3 cross 2 matrix because there are 3 inputs here and 2 outputs, right? So there are a total of 6 connections here. Okay, so let me just erase these numbers here so that it's easier and less cumbersome. All right, so this is W2 and this is 3 cross 2, and here you have weights 3 that are 2 cross 1. Right, so this weight here, so let me change the color here slightly. This weight, this output here is called O31. O31 is same as yi hat. This output here is O21. This output here is O22. This output that you get from here. But the weight on this neuron, okay, let me use a different color here. The weight on this neuron is W3. So because it's in the third layer, this weight is in the third layer. That's why W superscript 3, it's going from the first neuron here to the first neuron in the next layer. So 1, 1. This weight here is W3, 2, 1, because it's going from second neuron to the first neuron. Similarly, this weight here is W2, 1, 1. This weight, right? This weight here is W1, 1, 1, right? So if you see this weight here is W2, 2, 1. Similarly, this weight here is W2, 3, 1, because it's going from third neuron to first neuron. Okay, it's going from third neuron in this layer to first neuron in the second layer. So that's how we represent these weights. Okay, having understood this, now let's try to pose this problem as an optimization problem. Step 1, right? If you want to train, see, look at it. What are the unknowns here? At the end of this training, so you're given a data set B of xi's and yi's, right? And you have to determine the weights. What are the weights? W1, 4 cross 3, W2, 3 cross 2, and W3, 2 cross 1. So how many weights are here? There are 12 weights here, right? There are 6 weights here, and there are 2 weights here. The total of 20 weights, right? What does training a multi-layer perceptron mean? Training basically means computing these weights, right? So that's what training eventually means. Just like in your single neuron model. In your single neuron model, you're trying to find all these 4 weights. Here, instead of just 4 weights, you have a network of weights. You have almost 20 weights here, right? And we want to compute them. So step 1, let's go step by step, right? First step is define a loss function. So let me write my loss function as squared error, right? Summation over I equals to 1 to n, right? Yi minus yi hat square plus some regularization. Okay, the regularization is on the weights, right? This regularization is on the weights, right? Any random weight here can be represented as W with a superscript k and subscript I comma j. Right? Any weight can be represented as wk ij. Right? So typically your regularization will typically look like this. It will look like summation over I comma j comma k. All the possible values of I, j, k, right? Take the w, take the square of this. This is like the equivalent of L2 regularization, right? This is like your L2 regularization. How will the L1 regularization look like? It will look like summation over all the valid I, j, k's, right? Absolute value of ij, right? This is your L1 regularizer. This is how your L1 regularizer look like. But just ignore the regularization for now so that the optimization becomes simpler. Okay, because we understand regularization from logistic regression, etc. But just as a note, this is your L2 regularizer. This is how your L1 regularizer looks. And this is your loss function, right? And what is this? This is your simple squared loss. This is your squared loss. So just for simplicity, let me call Li as the square difference between just one point, right? So if Li is for the ith point, the square difference between actual value and predicted value, then I can write L as nothing but summation over I equals to 1 to n Li plus regularization. Right? I'm just defining a new term here. I'm just defining a new term. Right? This is my squared loss with regularization. How will my optimization problem look like now? My optimization problem will say minimize the squared loss, because you want to minimize the distance, you want to minimize the squared distance between your predicted value and your predicted value and your actual value. These are your actual values and these are your predicted value of y. So minimize L, right? L consists of squared loss. So L has two parts. L has squared loss and it has a regularization. But what are the variables here? Your variables are your matrix W1, your matrix W2 and your matrix W3. Right? In other words, I can write this optimization problem as, minimize over all Wkij's for all possible values of Kij. These are the variables that we will change. Minimize L, right? Where L is nothing but the sum of squared loss and regularization. This is the optimization problem we want to solve. So everything or most things in machine learning, especially in deep learning, boils down to your optimization function and simple chain rule of differentiation. Okay, that's the elegance of it. Some of the most important techniques in deep learning can be boiled down to simple calculus. So let's go to step 2, right? We have defined a loss function. This is our loss. We have defined an optimization problem. Very good. So what is the third step? The third step is your stochastic gradient descent or any gradient descent. Stochastic gradient descent batch or single point is when you are trying to compute. So suppose you're trying to compute this. Whenever you're trying to compute this, right? Instead of using all the points, if you're using a subset of points, that's called SGD, or else it is standard gradient descent, right? So let's keep that detail aside for a while. First step in any gradient descent based algorithm is initialization. Initialization of variables. What are your variables? Your variables are Wkij for all values of Kij, for all valid values of Kij. So initialize Wkij randomly. Of course, I'm just hand waving here. We will understand how to initialize the weights in a multi-layered perceptron in more detail in one of the future videos. There is lot of techniques. There are lots of very fine techniques. There are lots of techniques which help you build better deep, which help you train your deep learning systems or neural networks efficiently. Right? We'll come across these. They all are different forms of random initializations, but smarter form of randomization. Okay, we'll come to them a little later. But for now, let's just say you have to initialize them. That's first step. Second step is, how do you update any weight? Take any weight, for example, right? So if you have any weight, if you have any weight, let's say, suppose you have a weight Wkij, right? And what does gradient descent do? It iteratively keeps changing these weights in a for loop like structure, right? So the new value in the loop is Wkij, the old value, minus eta. Eta is your learning rate, right? We saw all of this in the linear regression and optimization chapter, where we understood SGD. So if you have forgotten, so this is called the update rule. This is called the update rule in optimization or gradient descent specifically. Then you have to compute the partial derivative of L with respect to Wkij. Right? So when you initialize it, which means at iteration 0, you will have a random value. Right? So at iteration 0, you'll have a random value. You'll compute the new value by taking the old value and subtracting with of course, this is called the learning rate. Okay, there is a lot of interesting theory on how to choose learning rates and how to vary them. We will discuss them in a lot of detail later in this chapter and the next chapters. But the most important thing that you have to compute, if you notice here, is this partial derivative. It is derivative of L with respect to Wkij. This is the most important thing that you have to compute. And this is the crux of this discussion. Because once you know how to compute this, you can keep updating these weights, right? And you'll keep updating. So the next step is do step 2, perform updates till convergence. And as we learned earlier, what does convergence mean? Convergence basically means you keep changing your wkij till the time the wkij old and new are almost very close, right? Because this is an iterative algorithm, right? You keep looping this. You keep doing this step over and over and over again, right? You keep doing it till the time your old and new difference becomes extremely small, or in other words, this becomes very close to 0. Till then, you keep updating your wkijs. That's what it means by convergence. Convergence basically means the old value and new value are very close to each other. Now, the most important step in this is to compute this partial derivative. That is the core discussion that we'll go through step by step, right? So let's take an example. So we have some of these weights here. So let's follow some of this. So first, let's take this weight. Okay, let's take this weight, right? So I'll erase some of this so that I can reuse this space, right? So I'll erase some of this because I want to show it to you graphically so that it becomes much more clear for you. So I want to compute now derivative of L with respect to W311, right? This is what I want to compute. Now see, W311, it goes into F31 and it impacts output 31, O31. This O31 is nothing but yi hat. This O31 now goes into your loss function, right? So if you follow the flow of this, your W31, again, let's understand this. Your W31 impacts your O31. Your O31 impacts your loss. Okay, that's what I've written it as hops here. Okay, so I can write this as derivative of L with respect to O31. And what is O31? O31 is nothing but yi hat, right? And derivative of O31 with respect to W311. Because O31, look at these two hops. This hop is represented by this one. So let's call it hop 1. This hop 1 is represented by this. This hop 2 here is represented by this, right? In hop 1, O31 impacts your loss function. That's why you're computing the derivative of your L with respect to O31, your output in 31. Now O31 is also impacted by W311. So that's why I write derivative of O31 with respect to W311. Very simple. Okay, so let's write it on a fresh page. Okay, so now we are computing all the W3s, right? Because if you notice, these weights are W3s. First we'll start with this, then we'll go here, then we'll go to weights in the second layer and weights in the first layer. Okay, we'll go step by step. We'll go backwards. Okay, so O311, derivative of L with respect to W311 equals to derivative of L with respect to O31 and derivative of O31 with respect to W311. This is simple chain rule. This is very simple chain rule, right? Nothing very fancy here. Very straightforward. Similarly, now let's go back to a diagram. Okay, I'll erase this, right? I'll erase this. Okay, I'll also erase this notation here. Okay, now let's go. Now I want to look at W321. Okay, so W321 it also impacts O31 and O31 impacts L. So I'll write it as derivative of L with respect to W321 is equal to derivative of L with respect to O31 multiplied by derivative of O31 with respect to W321. Again here, this is step 1 and this is step 2. This represents step 1 and this represents step 2. I'm just following the path here. If you notice, this W31 impacts O31 because this W31 is input into F31 which generates O31. This O31 is used. O31 is nothing but yi hat, right? Yi hat here is used within the loss function to compute the final loss, which we want to minimize, isn't it? So again, let's write it on a different sheet here. Very, very simple mathematics here. Derivative of L with respect to W321, right, is equal to derivative of L with respect to W301 and derivative of O31 with respect to W321. This is also simple chain rule, nothing very fancy here, right? So we got W3. Okay, so in the next page we will try to compute the values of W2, right? So again, back to our drawing board here. Okay, so we have gotten this. This is cool. This is good. So we have solved this. We have solved this. We'll just slowly erase this. Okay. Okay. So let me erase this clearly. So this is done and this is done. Now let's look at it. What about W211? Right. So derivative of L with respect to W211. Now if you notice, here is a very interesting leap. Your W211 goes into F21 and impacts O21, right? It impacts O21. This O21 goes into F31 and it impacts O31. Your O31, which is nothing but y hat, goes into your loss function and it impacts the loss function. So there are 3 steps here, 1, 2, and 3. Okay, let's write down those steps, right? So what is the third step here? Derivative of L with respect to O31. So derivative of L with respect to O31. What is the second step here? Right? What is the second step here? Your O31 is impacted by O21. So derivative of O31 with respect to 21. And your O21 is impacted by W211. So derivative of O21 by W211. Again, simple chain rule. It's very, very simple chain rule, right? Again, remember I told you a trick that I learned in my 11th class, right? So these two, I mean, of course, this is an incorrect way of remembering it, but to just check if the equation that you have written is right or not, these two are the same, these two are the same, and this by this is what we want here. So makes sense. This is like a sanity check. This is like a sanity or correctness check that I often perform when I write any chain rule equations. Very, very simple, right? So let's go ahead and write this on a fresh page. So derivative of L with respect to W211 is derivative of L with respect to O31, O31 with respect to O21, and O21 with respect to W211. Again, simple chain rule, nothing fancy, very, very simple stuff. Now similarly, right? So let me erase this now, okay? I mean, just by erasing it here, I can use this space more efficiently. That's what I'm trying to do. Okay, I'll just erase this, I'll erase this. Okay, so very simple. So this is done. Now what about this edge? Let's look at this edge, right? Which is W221. So let's do derivative of L with respect to W221. Your W221, right, will impact O21 because it is input to F21, right? So this impacts this, and now this impacts this, and this impacts this. So this is first step, second step, and third step. Okay, so let's write it again. So derivative of L with respect to O31, right? And O31 with respect to O21, right? And O21 is also dependent on W221. So W221, simple. So this is also done. Okay, so I'll try to erase this. This is a slightly tricky thing to erase, but I'll try to erase this. Okay. Okay, so let me just use the correct connections here. So this connection here, this connection, this connection, this connection, and there is an edge here. There is this, and this is O21, right? And this edge here is W221. Similarly now I can also write for W231, right? It is nothing but from here. So because this edge, right? This edge impacts this output because this is going as input here, right? It impacts this, and this impacts this, which impacts the other one, right? So I can write the same thing even for W2, 3, 1. Okay, so I'll write everything in a single page. Okay, so derivative of L with respect to W2, 2, 1, right? W2, 2, 1 is derivative of L with respect to O3, 1, O3, 1 with respect to O2, 1, sorry, and O2, 1 with respect to W2, 2, 1. Similarly, derivative of L with respect to W2, 3, 1 is derivative of L with respect to 3, 1, derivative of 3, 1 with respect to 2, 1, and 2, 1 with respect to W2, 3, 1. So these are the weights in W2. Right? Of course, we have only covered these 3 weights. Similar thing can be done for this weight and this weight and this weight also. I'm just not doing it right now. Okay. So 3 weights, there are total of 6 weights here, right? For 3 weights, we have written the equations here. This is all W3 weights. These are 3 weights of the 6 weights in W2. Okay. So you can write similar equations. It's very, very simple. I recommend you try and do it on your own. Okay. Now let's go to W1, the fun part here, right? So all this is well and nice. Okay. So, okay. When you go to W1, so W1 are these weights, right? So let's take this first example. Okay. Let me change the color here. So let's say this is this is W111, right? So let's write it down. This is a slightly more tricky case. Okay. So what is derivative of L with respect to W111? Now, if you notice W111, right, impacts. Okay. So let me just erase this slightly so that it becomes easier, right? I'll just erase this and redraw it because there is a lot of notation here which is cumbersome. I'll just erase this quickly and rewrite some of these. Okay, let me just erase this. Okay, so I have F21 here and F22 here. These 2 things go as inputs here, right? So this goes here and this goes here. This is F12. This goes here and this goes here. This goes here and this goes here. So let me color the outputs. This is O21. This is O22, right? This is O11, right? And this is also O11. This is also O11, right? So now let's look at this. This is very interesting. Your W111 impacts O11. But O11, instead of going only to F21, it is also going to F22 here, right? So just let me write it clearly here. This is F22, right? So your O11 is going both into this and into this, and into this. So there are 2 paths it's taking, right? And your O11 impacts O22 through this chain, right? Through this chain it impacts O22. Through this chain it impacts O21. And O21 impacts O31, but O22 also impacts O31, and O31 impacts L. So till now, we have seen only one path. Here you have 2 paths, if you think about it, right? You have 2 paths. So let me just erase this. That got a little tricky, but let me redraw some of these things. Okay, so this is F11, this is F12. There is an edge here, there is an edge here, there is an edge here. There is an edge here, here, and here. Okay, so this is O11. This is also O11. Okay, so this O11 impacts O21 and O22. So this is a slightly tricky case. So let me explain you something in calculus. Okay, very, very nice idea in calculus. Very, very simple idea. So imagine I have a variable x, right, which goes and impacts a function f, right? So you have f of x, right? Suppose this is a function of x. You have x which can also be input into g. This is g of x, right? Now let's assume I have a function h, and this h inputs, it takes f of x and g of x. Okay, and this outputs something. Let's say this is how it works. X is now input into f of x, generate some output, right? X is input into g of x, it generates some output. These outputs go into h of x, right? This is exactly the same situation that we have. We have two paths from x to h, right? If you notice here, if you notice this diagram here, we have two paths. One path is like this. Just follow my cursor here. One path is like this. The other path is like this. So there are two paths, right? So one path is directly impacting this. This also impacts this, and this goes and impacts. This goes and impacts 2, 2. 2, 2 goes and impacts 3, 1. So there are two paths to your O31, right? This is exactly the problem that we have here also, right? There are two paths. There is one path like this through f. There is another path like this. In such a case, derivative of h with respect to x, again, this is also a chain rule. This is a special case of a chain rule, is derivative of h with respect to f and derivative of f with respect to x plus derivative of h with respect to g and derivative of g with respect to x. Here, this is so because your h is a function of the outputs of f and g of x, right? So if f itself is a function of outputs of two other functions, right? So derivative of h with respect to x is, this is one path, right? What is this? This is nothing but this path. This is nothing but this path, right? What is this? This is nothing but this path. So you take the derivatives on both the paths and sum them up, and simply sum them up. This is also a special case within the chain rule. It's a slightly more intricate form of chain rule. Okay, so we'll apply this now. We'll apply this slightly intricate form here because there are two paths here, right? First, let's take this path. Okay, this is step 1, step 2, step 3, step 4. Okay, so let's write the first step. Okay, derivative of L with respect to O31. This is step 1. O31 with respect to O21. O31 with respect to O21. Sorry. Okay, and O21 with respect to O11. O21 with respect to O11. Right? Simple. Okay, so let's write this. Okay, it's a slightly tricky one here. Sorry. So let's write it this way. Okay, take it step by step actually. That will make the problem fun. Okay, so if I say dl by do31 into do31 by dw 111. This is fair, right? I can write this like this, right? Now the challenge here is how do you compute this? So this is straightforward, right? This is straightforward. We have been seeing this. This path. So this is step 1, right? This is step 1. Now, if you notice this step 1, okay, let me actually write it. This is 1, 2, 3, and 4. Let me number this. This is 5, this is 6, and this is 7. Okay, this step 1 is common, right? This step 1 is common between both these paths. So what we have here is a slightly different structure from what we saw here. What we have here is you have x, you have f, you have g, you have h, and you have, let's say, some function k here. Okay, this is the structure that we have actually. Because if you notice the structure in the graph here, the paths diverge here, but then from here onwards it's the same path. Okay, so which is exactly what we have here. In this diagram, the paths are different till here, but here the paths converge. In this case, what is derivative of k with respect to x? Okay, let's ask that question. It is derivative of k with respect to h and derivative of h with respect to x. Fair enough? First step. Okay, so I finished this step. Okay, let me color it differently. So I finished this step. This step is this. Now I have to figure out how to compute derivative of h with respect to x. How do I do it? I've computed it earlier, right? Right here I wrote it. So derivative of h with respect to x is derivative of h with respect to f and derivative of f with respect to x plus derivative of h with respect to g and derivative of g with respect to x. So overall derivative of k with respect to x is derivative of k with respect to h multiplied by derivative of h with respect to df, df by dx plus dh by dg, dg by dx. Okay, let me explain this for those of you who have lost me here. Okay, this part I simply copy pasted here. This part is nothing but this summation, and this summation is what I have in these curly braces. Simple, right? So the same thing, that same structure that we see here, we will reuse it here. Okay, so let's break this down. So we have derivative of L with respect to 3,1. Now we have to compute this. Now we have to compute derivative of 3,1 with respect to, okay, so this is the challenging part, right? So let me write it down here carefully. So derivative of 3,1 with respect to this is, because O31 has this path, 2, 3, 4 path to this, to W111. It also has 5, 6, 7 path. Okay, so let's write down first 2, 3, 4 path. Okay, it is derivative of O31 with respect to 2,1, derivative of O21 with respect to O11, right? And derivative of O11 with respect to this. So here, again, let me number them, right? This is step 1. Okay, this is step 2. This is step 3. This is step 4. Step 2 is here. Step 3 is here. Step 4 is here. Step 1 is here. Right? But derivative of this is not it. Because there are 2 paths to arrive at O31 from W11. Right? Just like in this case. In this case, there are 2 paths to arrive at H. That's why we have taken both these summations and added them up. Right? Similarly, here in this diagram also, I finished my 1, I finished my 2, I finished my 3, I finished my 4. What I'm left with? 5, 6, 7. So let's write them down. It's derivative of O31 with respect to O22, right? And O22 with respect to O11. Sorry, O11, and derivative of O11 with respect to W11. Right? So this, I have it here. This is exactly what I have here, right? So now if you put everything together, what do you get? Let's write it down. It's slightly tricky, but let's write it down. Okay? So for W1s, right? So for W1, what do you have? Derivative of W11 is equal to derivative of loss with respect to O31 multiplied by derivative of O31 by O21 and O21 by O11 and O11 by W111 plus derivative of O31 by O22 and O22 by O11 and O11 by O11. This is a slightly complex one, and you have this summation because there are 2 paths, right? And imagine this is only for a neural network which is of depth 3, right? Because you have an input layer and you only have 2 layers. This is layer 1, right? And this is your layer 2. This is your output layer. Imagine a neural network with 10 layers, right? There will be these chain rule. You apply the same chain rule. There is nothing magical about it. It's the same chain rule. You just apply it over and over and over again. That's all you get, right? Very, very simple, very, very straightforward. So now we will use, so this is only the first part, right? And remember, once you can compute these derivatives, once you have computed these derivatives, you can quickly update your weights. But we'll learn something called a technique called memoization, which will make it more efficient. We'll learn it in the next video. But this is the core concept. Don't get lost just in derivatives. Look at the big picture. The big picture is this. The big picture is you initialize all of these weights randomly, and then you update each of these weights by leveraging the derivative. This is why we computed it. Let's not forget that, right? And we have shown how to compute the derivatives for any of these weights. We have seen how to compute derivatives of weights which are in 3rd layer, which are there in 2nd layer, which are also there in this 1st layer. Okay, I wanted to show each of these examples one by one. That's why I've taken slightly more time than what I would prefer for a single video.